What's up, guys? This is a quick video showing how to do a torque problem for those of you who finished the 3.1 worksheet today. And so I wanted to just kind of go through this real quick because not everyone made it that far in the notes. So let me get it where I can annotate. So you'll notice here at the top, we talked about how torque is a vector quantity, which means the direction matters. And clockwise, as we mentioned, is the negative direction, whereas counterclockwise is positive. And so if an object's going to be in rotational equilibrium, like this sign here, at Jen and Eric's store, generic, you'll see that the torque clockwise is going to be equal to the torque counterclockwise. In other words, the sum of torque is equal to 0. And so everything going in one direction is going to be balanced out by something going the other direction. So if they tell us that we have a 350 Newton store sign hanging from a pole of negligible mass, that means we just are ignoring the fact that there's a pole. The pole is attached to a wall by a hinge and supported by a vertical rope. We want to know what's the tension in this rope. And so if I think about this rope acting here, there's a certain gravitational force from the sign. And then over here with my pole, which I know this dashed line is kind of overlapping it, but it says there's a pole here. And so that's providing an upward force. We could call that a tension. And then on the hinge over here, there's also going to be an upward force. We can just call it force sub y that's providing the strength to kind of hold up the sign. And so if this thing was removed, we know that the sign, of course, would crash to the ground. And so that's kind of the scenario we're looking at. So to set this up, all we have to do is remember that the sum of torque is equal to 0. So we can always just set the torque clockwise equal to the torque counterclockwise. And if we look at that in the clockwise direction, we can think about which of these forces is acting like in a circle, almost like a clock moving. And if we kind of think about Fg, if it was allowed to swing this way, Fg would be going in the clockwise direction. And so I can put Fg. But remember, torque is not just a force. Torque is equal to force times distance. And the distance that is 1.3 meters away from my hinge, which is right here. Sometimes it's helpful to put a little X on your hinge to remind yourself that it's an immovable thing. Let me remove that X so it's not confusing. And so if I go from that X to my distance of Fg, it's 1.3 meters. So that would be times d1. That's going to be equal to the torque provided by my pole over here, which would be tension times d2, and that distance, of course, would be the full 2 meters. So if I plug in my values, they want to find the tension in the ropes. If we rearrange, we would have Fg d1 over d2, which means we would have 350 newtons times d1, which is 1.3 meters, all over d2, which is the full 2 meters. And if I crunch the numbers, I get about 227.5, so 228 newtons. Now we'll notice that the tension here is not equal to the weight of the sign. And the reason why is because that tension is all the way at the end of the pole, and so it doesn't have to do as much work to counteract the weight of the sign, which is in the middle of the pole. And we're also not considering here the forces on the hinge. On the back side of these notes, we would actually go and find the force on the hinge, but we don't have to do that yet. In order to get you started on practice, this should be everything you need.